Okay, so good afternoon. We can start. Okay. Okay. So I want to start by reminding ourselves where we are. So this is kind of where we are. Just that we won't lose track. So this is the list that I discussed. It's on, no? Oh. Can you hear me up there? Wow. This says that it has battery. How about this one? That's better. Okay. Okay, so again, this is just a reminder of where we are. And really what I want to talk about is, I'll use this one instead. I want to start talking about a few issues. So first, this box here, well, I can erase registration from the list. I don't think it's a problem anymore. A few issues on homework one. So one issue that I know that a few of you, a small number, maybe 2% of the people had complaints about the need to use LaTeX. So we talked about it. So my perspective is that we gave you the template. It's much, much better than using Word if you want to write math. And so you'll thank me after the class once you be fluent. And in general, I think that, you know, as computer scientist or computer scientist to be, it shouldn't take you more than a few minutes to fight with it. There's a lot of advice on the web if you have a problem. So I think this will not be something you'll spend most of the time on. I think you'll spend maybe up to 15 minutes, half an hour fighting with this. So should be okay. I want to remind you the late policy. So the late policy is that you have 96 hours after tonight. Hopefully you won't use it because you won't need it and you'll save it for later in case something happens. But just that you know that's a fixed policy. Questions about the homework? Okay, okay, excellent. Question. Specifically, in what, which question are you talking about? So I think, I don't remember exactly how we phrase it, but I think that you can explain how you do it. At the end, there's going to be a numerical answer. Which part of question 3? Yeah. So I think it would be good if you explain. It will be good for yourself also if you explain what is the mapping between the notation that we used in the linear program and the notation that you're going to use. What's going to be the B, what's going to be the A, what's going to be the C, and so on. So, other question? Okay, so tonight we're planning to, tonight or tomorrow morning, we're planning to issue, to put out the second homework, One thing that I wanted to say about it, so the TAs are going to talk about it in the next few sections. It's about decision trees. In fact, I said something about what it's going to be. It's decision trees where you will learn small decision trees and then learn a linear function over the small decision trees. So hopefully you will figure out advantages and disadvantages of learning one simple function versus using it as features for another functions and so on. One thing is that we'll ask you to do experiments. So one of the key lessons that I want you to take out from this problem set is that machine learning is an experimental field, and you need to figure out how to do experiments. So you don't want to sit there and, type every time you want to run another experiment. You want to be organized, write scripts, figure out what you do. And at the end of the decision tree lecture notes, I had a few slides that I did not cover, and they would introduce some of the notions that you need for this problem set. Running cross-validations, doing t-tests, and so on. Everything is also introduced in the body of the problem set, but you can consult the lecture notes also. Okay, finally, so we talked about mechanism that I wanted to introduce for kind of getting you a little bit more involved, although so far I really appreciate that you are involved in the class and it helps me and helps you. So what we're going to do, because there are too many of you to do exercises in class, we're going to try to do exercises on Compass. And the idea is going to be that we'll give you a simple exercise that will be built on something you've seen and will introduce what we're going to do next. And we'll give you a deadline by which time you need to do it. And people will get 1%, an additional 1% if they do this. So hopefully you'll spend the time. It's supposed to take 10 minutes, I think. So the first one is going to be available tomorrow after you're done with the homework. And I'd like you to finish it before next class, before Thursday. So it will be available on Compass. We're going to put a note on the web page and going to put it on Piazza so you'll know that you can look at it. Yeah. No. So the question was whether further homework will involve MATLAB, and the answer is no. Although in some cases you can choose whatever you want to do, so you could choose to use MATLAB. Other questions? Okay, so I want to talk about the project. I got a lot of questions. So I actually decided to move forward the proposal day. I think it's going to be helpful to all of us. So it's going to be in a few weeks, October 9th. Hopefully it's true that it's a Thursday. And basically for a proposal, what I want is just a single page, or 1 to 2 pages, because it's very difficult for you to write one page, that explains what you want to do. But the key requirement is that you will already have spent some time thinking about it, reading about it. So the key issue is that I want you to include references. So one of the key requirements from this project is that you read a couple of papers or more. And I want to see that you know what are the relevant papers, or what are some of the relevant papers to your project already in the proposal. So other than that, anything that has to do with machine learning or as a significant component of machine learning is okay. You can do experiments, you can do theoretical work, you can do a combination, you can do a critical survey of a topic that you want to learn about in machine learning, anything you want. And really, the only hope is that it will be interesting. So you'll do something that you care about and will be interesting to me also. So I have some ideas that I can propose. So one idea, again, this was mostly triggered by the fact there are many of you that want to do projects. So one possibility is to participate in a machine learning competition. So the suggestion here is to participate in a competition that is already passed, but still, it's an interesting competition. So KDD Cup 2013 had two interesting competitions that are described here, and there are pointers here. It's not easy to build a very good system for these two tasks, and you'll see the papers that people have written. A lot of detailed and hard feature engineering work, but still it's a very interesting thing, and it will teach you a lot about this specific area, but in general about experimental machine learning. Now, you don't have, so if you like this idea, you don't have necessarily to participate in the task. You can slice a project out of it and define it and do it, or you can participate in the task, in which case we're probably going to provide you a new test data in addition to the one that is provided in the task. But this is not the only option. So this is one option. You can think about, and these are just random suggestions. You can come up with others just to show the diversity of the possibilities. You can think about, how do I make a learned hypothesis, for example, a linear threshold function, more comprehensible? So forget what's in the parentheses there because I decided not to include the details. You can develop a people identifier. So people come to my office, and I want to see a sign in my office that says, this person is approaching. Do it in a multimodal way. You can compare regularization methods or compare algorithms that deal with different notions of sparsity. You can do large-scale clusterings of documents with the additional interesting component, which is name the cluster, which is not so trivial. You can play with deep networks. One possibility with deep network, take a natural language processing program and convert it to a deep network. There are some issues that are involved in how to do it, how to make it efficient. The advantage eventually is going to be that you will not have to spend a lot of time on feature extraction at evaluation time. So at evaluation time, it will be faster. Could be a very interesting project. Again, any of these projects or others, if you have interest in it, come and ask me questions.
What extent do you use toolboxes? For example, if I want to do something on decision trees, so how do you write that entire?
So the question is, to what extent can we use toolboxes? You can do whatever you want. So the idea is that it's going to be a research project. It does not mean that everything has to be developed from scratch. In fact, if you will want to develop everything from scratch, you'll probably won't have time for the research. So definitely, some of the building blocks, if they exist, use them. Final point, try to prove something. And again, anything that you're interested in the machine learning area. Questions? Okay, so basically the key thing is October 9th. Please do send me email or ask me questions about options that you have or ideas that you're thinking about. Okay, so we want to talk about Perceptron. Just to remind ourselves what we did last time. So we started talking about possibly one of the most important learning algorithms that we call Perceptron, and basically we said that it's a mistake-driven algorithm that takes a sequence of examples. Given an example, it predicts on it, given its current model, current weight vector. If there is a mistake, it updates the weight vector. And it can do it in two ways. If the example is positive, we're going to add the example to the current weight vector. If the example is negative and we made a mistake, we're going to subtract it. Very simple algorithm. And we gave an example of how this would run, and I had a mistake. Someone pointed out after class that I had a mistake in this, and I clarify it now by saying that red is positive and blue is negative. With this, this works. So this is where we were last time. So just to summarize, so we have a weight vector. Let's say we initialize it with a 0 weight vector. We cycle through all examples. You can randomly choose examples if you prefer this. And then we predict the label of an instance X to be the sign of W dot product with X. So it's either +1 or -1. If we made a mistake, right, so Y prime that we predicted is different than the Y that is supplied to us, the feedback, then we update the weight vector, and we update it this way. The new weight vector is the old weight vector plus some learning rate times Y product in X, of X. So X is the vector, Y is ±1, which means that we either add X or R times X to W or subtract. Okay? Otherwise, if there's no mistake, we just don't change the weight. So we had two comments. One important comment is what happens if the X's are binary, which is the case in many, many applications. And in this case, it's kind of interesting because basically it means that weight coefficients of the weight vectors that correspond to X's that we don't, that are 0, that are not active in this example, we don't touch them. And we briefly said something about why this is important. Why is this important? It's very important when the X vector is very sparse, where you have a lot of dimensions, but very few of the features in the X vector are active. Because then it means that you're going to just, you represent the X in another way, not just as a huge weight vector with a lot of zeros, and you do it in such a way that will allow you to just touch those W's that correspond to the active X's. And the other thing that we said is that we can think about this update rule, Wx greater than 0, in an equivalent way this way, and I'm going to come back and revisit this later today. Okay. So question so far. So the algorithm is clear. So what I want to do today is I want to prove a few things about this and maybe another algorithm. So hopefully you have your thinking cap here. And basically trying to understand why is this such a good learning algorithm. Okay, so just a few general things. So clearly what we're trying to do here is we're trying to learn a linear separator. So you could say, well, obviously, all we can do is linearly separable functions, right? Because we're trying to learn a linear separator. In fact, we'll see that it's a little bit more general, right? So we do learn a linear function, but maybe it will do okay also for functions that are not quite linear. Now, an important historical note, especially important, I think, these days, is so Perceptron, as I said, is an algorithm that was studied in the 50s and started in a research area that had to do with perceptron and also with neural network, kind of multi-layer perceptrons. In '69, a book by Minsky and Pepper came out that is called Perceptrons, very influential book, that shows that perceptron cannot learn things that it's not supposed to learn. Basically, that it has representational limitations. So they show that parity functions cannot be expressed by perceptrons. You know this already, right? Yes? They show that, this actually can be cast in a more application interesting ways. For example, in vision, if the patterns that are represented only with local features, then you cannot represent interesting properties like symmetry or connectivity using this. So it's a very interesting book. And in fact, I suggest in the early 90s, when I was a student, a new version came out of this book. Very interesting book with a lot of handwritten comments by Minsky on the original book. So it's still a very good read, so I recommend, if you're interested in these issues, try to get it. But the impact was, at that time, that the research on neural networks stopped for years. So this book really was misunderstood and impacted funding for many years. It came back in the late 80s. For people that know, there's a PDP book or a series of books that are called PDP that brought back neural network, and then it died down again in the 90s, and it's up again, if you haven't heard. Now it's called deep learning. So this is kind of the wave of these things. But in fact, Rosenblatt knew what was written in the Perceptron book. He actually says in his original book that the interesting problem, given that we believe the usefulness of this algorithm that he developed, the interesting question is, what pattern recognition problem can be transformed so as to become linearly separable? So he actually had this picture in mind, the picture that I showed a few lectures ago, about mapping from a problem that is not linearly separable to a problem that becomes linearly separable by transforming the features. He had this perspective, and he talked about it. So the discoveries in the book were actually, from his perspective, irrelevant. But, at the end, he actually died a sad man because he didn't see the success of his life work. But here are some of the things that he knew. So he knew that if there exists a set of weights that are consistent with the data, another way of saying that the data is linearly separable, then perceptron will find it, will converge to it. Not to it, will converge. He didn't study the question of how long it would take, and we want to understand this. But he knew that it's going to converge. He also knew that if it's not linearly separable, it will not converge. It will basically cycle through the data. But again, the question is it going to be good? And we're going to address it. Okay, so my goal now is to actually prove that perceptron is good under a very specific definition of good. Before that, I want to show another way of writing perceptron. This is the same algorithm that you've seen before. We initialize it. In this case, I'm writing it as a weight vector and a threshold. So remember the trick that we had of adding one dimension and eliminating the threshold. I'm writing it here with the threshold, just that you will see that when we update, we actually update the threshold. So we don't fix a threshold, we actually update it. Basically, when you have an n+1 dimensional vector, you're going to update all n+1 dimension. And it's important to understand this and not think that the threshold is fixed and we are updating the other things. Okay. So with that, let's try to prove something about perceptron. So one thing we did last time is we introduced this notion of mistake bound. That is, we said, here's a learning algorithm. The learning algorithm is going to be an online algorithm. So it's going to take an example, make a prediction, get feedback, and keep on going. And we asked the question, is the algorithm going to stop making mistakes at some point? Remember? And it's an important question because you want your learning algorithm to stop making mistakes at some point and do well. And we actually proved in some setting a mistake bound for some algorithms, right? But the assumption there, just because we wanted to make it easy for us, what was the key assumption when we did this consistency algorithm or halving algorithm? What was our key assumptions when we proved that this algorithm is going to stop making mistakes? Finite hypothesis space, right? So we said, let's think about a collection of Boolean functions over n variables. So it's a finite hypothesis space. It's a large hypothesis space, right? It's going to be double exponential in n. But it's still finite. And under this assumption, we proved that the number of mistakes the algorithm is going to make is bounded. Interesting, but maybe expected. What we're going to do today, and I kind of hinted on it last time, is we're going to prove something a lot more interesting. Now, when we're trying to learn linear functions, the hypothesis space is infinite, right? Nevertheless, we're going to show that the algorithm is mistake bounded, which maybe is a little bit surprising, right? Because you could imagine, I can always move it a little bit. And maybe I will always have to move it a little bit. So under specific conditions, we're going to show that there is a mistake bound. So let's see what we can show. So we are dealing with perceptron. We are maintaining a weight vector of real valued W in Rn here. We're starting with the vector 0. And this is the algorithm, right? You know this. What is the theorem? So the theorem we're going to prove is this. This is the theorem of Novikov, a Russian mathematician. You can see early 60s. So all this was somewhat understood then. So here's a collection of examples. So we're given T examples, labeled example, x, y, with xi in Rn, right? So the feature vectors now are real valued numbers. That the size of each example, this is L2, okay? The sum of x of the square of the feature vectors, square root. Just the size of the example is bounded by capital R. Is this a big assumption? Why is it not a big assumption? Because it's not a big assumption because this R exists, right? There is a finite collection of examples. Look at the size of each example. Take the max, call it R, right? This R always exists. So it's just a notational thing. It's not an assumption, okay? So this is why Y is -1 or 1. And I'm assuming that there exists a vector U and a gamma, a positive gamma, that satisfy the following condition. First of all, I'm assuming that U is equal to 0. Size of U is equal to 1. Again, not a big assumption because U is going to be my separator, right? Which means examples such that U times X positive is on one side, U times X negative on the other side. The size of U doesn't matter because if some U satisfies it, 7 times U is also going to satisfy it. Agreed? So I can agree that the size of U is 1, right? I'm going to shrink everything so that the size of U is 1. Okay? So that's not an assumption also. And I'm assuming that this is satisfied, that Y times the dot product of U and X is greater than this gamma. So again, is this an assumption? What kind of an assumption is this, if it is an assumption? It's separability, right? So if the data is linearly separable, then this gamma exists, this positive gamma exists. Again, I have a finite set of examples. So I can look at this for each one of my t examples, take the smallest distance to the separating line, and call it gamma. Okay? So, but nevertheless, this is a complexity parameter for me, because in some sense, it describes how difficult this data set is. If gamma is very, very tiny, it means that there are points that are very close to the separating line. If gamma is big, it means that all the points are farther away from the line. Right? So in some sense, it's a complexity parameter. It describes how difficult it's going to be to, when we do the learning, to kind of find something that splits the data to positive and negative. Okay? Okay, so under these conditions that you see, basically all I did is just described a linearly separable situation, right? Nothing more, nothing less. Then the perceptron is going to make at most R square over gamma square mistakes on this sequence. So again, what does it mean? It makes a lot of sense that our gamma square is here in the denominator, right? So as gamma becomes smaller, the data set is harder. So it makes sense that it's going to take me more time, or that I'm going to make more mistakes before I get to a separating plane. So it's to be expected. Okay, I'm going to put some additional notes, if it's not already on the web, just to give some more details on these issues. But we can actually prove it. It's, as you can see, it's a one-slide proof. So let's see. So what do we do? So let's assume that VK is the hypothesis before the kth mistake. Right? I already made k minus 1 mistakes. Now I have VK, and I made a mistake on VK when I had VK. And assume that this occurs on this example, xi, yi. What does it mean that I made a mistake? This is what it means. Right? Let's understand this. So basically, the dot product VKXI, its sign is different than YI. Right? So either YI is positive and the dot product is negative, or vice versa. Anyhow, this is negative. That's equivalent to saying that I made a mistake on this example. Agreed? Okay, so now we're going to do analysis in two parts. The first part, or first of all, let's say, before the analysis, once I made this mistake, I'm going to update. So VK plus 1 is going to be this, VK plus YIXI. That's the perceptron update rule. And now, with this, we can do analysis in two ways. So first of all, let's compute the dot product between VK plus 1 and U, which is the truth. All the time, I just want to keep my assumptions here. My assumption is, I'm going to use all of these, that I'm starting with 0 hypothesis vector, that the size of U is 1, and that I have this linear separability assumption. Okay? So let's think about what happens. So what's VK plus 1 dot product U? I'm just substituting the definition of VK plus 1 from here. So it's VK times U plus YI U XI. Right? Just substitution. Now I'm arguing that this is greater than this thing. So I just copied VK dot product U here. And then I'm claiming that this is greater than gamma. Why is that? Just the assumption of the linear separability. This is written here. Right? Okay. Now, I did this when I moved from VK plus 1 to VK. I can keep on going, right? So I can keep on going. Here I have VK plus 1 dot product U. Here I have VK dot product U. I can go to VK minus 1 dot product U, and so on. I can do it k times. Every time this says you're going to add 1 gamma. So overall, I can say that, and V1 is 0. So overall, I can say that vk plus 1 dot product u is greater than k times gamma. Okay? Step 1. Step 2, I'm going to look at the norm of vk plus 1. So again, this is vk plus 1 by the Perceptron update rule. So let's just compute the norm. So it's the norm of vk plus 2 times yi vk dot product with xi. I just take this and I compute the this times itself. So I get this term plus xi norm. I have yi xi, but yi is plus or minus 1, plus or minus 1, so the square is just 1. Okay? Then I argue that this is less than equal to this. So first of all, I copied vk norm. What happens with this? What can I say about this? This is negative because I made a mistake with vk when I evaluated it on xi. So I can just drop it and I get something larger. And xi square, we bounded it by r square. So I can say that this is less than this. And again, what happens? I moved one step from vk plus 1 norm to vk norm, and I added r square. I can keep on going. And every step, I'm going to add r square. So overall, vk plus 1 square is going to be bounded by k times r square. Okay? What did we get? So I'm just summarizing here what we got. So on one hand, I know that the norm of vk plus 1 is less than the square root of this. So it's square root of k r. On the other hand, it's greater than vk plus 1 u. That in itself, what I showed here is greater than k gamma. Right, so I showed this inequality in the top part. I showed this inequality in the bottom part. This is always true because the norm of u is 1 or less than 1. Okay? So just from the definition of dot product, this is less than the norm of vk plus 1. Okay, so we got it, right? So basically with this, what we get, just look at these two. So k gamma is less than square root of k r. Divide everything by square root of k, move to the other side, you'll get that k must be less than r square over gamma square. So the number of mistakes we are making is bounded by this. Okay? Somewhat magical, but really, really powerful. Questions? Yeah.
But maybe you won't exist, so that.
Okay, excellent question. So what we showed is that if U exists, if the data is linearly separable, rather quickly, as a function of how good the separability is, right? So how far are the points from the line, we're going to stop making mistakes. It still remains to say, you know, how well will Perceptron do if U does not exist, right? If the data is not linearly separable, basically. And we're going to address it in a second. Just one thing I want to say, because the data is linearly separable, there are infinitely many linear separators, right? Agree? We found one, and we stopped, right? Because it's a mistake-driven algorithm. Can we say something about it? Is it necessary? I mean, so let's assume the closest positive to the line is here and the closest negative to the line is here. There's a lot of things that I can put in the middle. Is there a way to say something about, you know, which one is better? Or are they all equivalent? Equal distance. So there is a suggestion to say, you know, if it's true that this is the closest positive, this is the closest negative, or a group of closest positive and a group of closest negative, it could be that the perceptron will find a line here, very close to the, what was this, the side of the positive, the positive examples. And, you know, maybe that's not ideal for the future. If I find something that is rather in the middle, maybe it's going to be better. Now, from the perspective of this analysis, doesn't matter, right? As long as I separate the data, it's fine. Right? So we don't care about our metric at this point does not involve the future. Our metric at this point is we stop making mistakes, we're happy. Maybe we want to think a little bit more about it and say, you know what, among all possibilities that separate the data, I want you to choose this one. Because I kind of feel, and maybe we can quantify, it's going to do better than just any separator. Is this intuition clear? Okay, so, but first let's address this question. So what happens if it's not linearly separable? Oh, before that, 2 notes. One important thing is that notice that this bound is magical, right? It does not depend on the dimensionality. It does not depend on the number of examples. Right? It basically says this is the number of mistakes you're going to make. That's it. And another thing which should be trivial to you already is that we place the weight vectors and the example in the same space, right? So they are all, you know, some dimensional vectors, n-dimensional vectors, and we add them and we subtract them and we deal with them as, you know, the same thing, right? It is important. It's important here, and it will also be important later when we think about other representations of the same algorithm. Probably next time. Okay, so robustness. So what happens if the data isn't linearly separable? So it turns out that a slight extension of this theorem, and in fact also a slight extension of the proof, but I will not show it, actually shows that perceptron is going to be robust. So let me just try to formulate it. So in the non-separable case, we need to quantify the extent to which the data is non-separable. And we're going to do this using this slack variable. So I'm defining the slack variable this way. It's the maximum between 0 and the difference between our gamma from before to this dot product. Notice that now I added the theta because it fits better my picture here, where I kind of move the linear separator from the origin. But it doesn't matter whether I have the theta here or not. Hopefully that is not something that confuses you at this point. So basically it's gamma minus yi dot product. Now, what does it mean that psi is 0? It means that this max is 0. It means that this is negative. Let's see. So this is negative, which means this is larger than gamma. Right? Which means that the points are outside this gamma thickness. Right? So I'm good. Okay? If it's outside, we're fine. So basically, psi equals 0 means that we have good margin, at least gamma. Otherwise, we don't have margin. So the points are inside this, or they went to the other side completely. Right? So this is the non-linearly separable case. So psi is going to measure how much we are not separable. We're not gamma separable, or at all we went to the other side. Okay? So what I want is I want to use this psi as my complexity for how many mistakes I'm going to make now. So, and the theorem says that the perceptron is guaranteed to make no more than, the 2 here is just technical, so R, which is the same R that we had before, the ball around the data, the size of x squared, plus D2, divided by gamma squared. So basically, what we added is we added this d to the r. And this d is sum of all the xi squared. For each example, we have xi. It's 0 if the example is OK. It's non-zero if the example is not OK. And I'm summing all these up. And this gives me another complexity parameter to how non-separable the data is. And as a function of this, we see that we still have a mistake bound. But if this is going to be bad, the mistake bound is going to be bad. Yeah. Oh, okay. So first of all, gamma here is not something we have to choose because it's just for the analysis, right? I'm just proving a theorem about gamma. Let's go back to the statement of the theorem. This gamma from the statement of the theorem is given to us. Look at the data. It's there, right? Because it's basically dictated by the closest point to the linear separator. Here I have to optimize, and I'm going to get to it a little bit later. But in the linearly separable case, it comes with the data, right? Here you have to choose it for the bound. So there is a trade-off, in fact, there between gamma and xi, right? If gamma is going to be tiny, xi is going to be larger, and vice versa. But they behave in a competitive way, of course, in this bound. So it makes sense. So again, this is an analysis thing. So for the analysis, you're given the data, choose it in the best way for the bound. Algorithmically, we're going to get to it in a second. There are some cases where you want to impose this gamma. Okay, but basically the point was here that actually you can prove bounds also for the non-separable cases. And it's as simple and as intuitive. The important thing is that you have two complexity parameters now, this gamma and xi. Okay, so before we go to extensions, I want to say a few other things and link it to some of the issues that we discussed last time. So last time we talked about Boolean functions. Specifically, we talked about disjunction, conjunctions, and we were motivated by this example of k disjunctions. I want to remind you what we said. We said if you have disjunctions or conjunctions, it's going to take you n examples if the dimensionality is n. But if I tell you ahead of time that I have k disjunctions, what was k disjunctions? Remember how do we define k disjunctions? Yeah? Right, so I know that I have n variables altogether, or n features altogether, but I also know that only k of them are important. So the hidden disjunction is going to have only k variables. I don't know which k. What we showed is that for these cases, there is a theoretical algorithm, the halving algorithm, that will make only k log n mistakes, which is really nice because it says if k is much, much smaller than n, we could be very happy. We don't really care about n. N could be, 20 million. If k is 100, we're going to scale linearly in 100 and only logarithmically in the millions, which is fine. The question is, can we come up with an algorithm, a practical algorithm that behaves this way? If you think about it, Perceptron isn't doing it. You can think a little bit about it, and you'll see that even for k disjunction, Perceptron, in fact, is going to make order of n mistakes. But, and by the way, it's a question here. So why do I say that Perceptron is going to make n mistakes? Before I said doesn't depend on dimensionality. And now I'm introducing n here. Where is the n coming from when I'm talking now about mistakes? Yeah? Okay, so R will be function of n. And also, what about gamma? Okay, so think about what is gamma in the case of this junction. Basically, think about the closest positive and negative examples that you can have, and this will give you gamma. Okay, so n, it's natural to see n there. So what I want to do is I want to develop another algorithm that actually can deal with it. And the algorithm is Winnow, which is a version of Perceptron that updates in different way. So I'm going to give an example here and do some analysis only for a special case, because the real analysis, the general case analysis is more complicated, but hopefully it will give you an intuition. So what is the, so first of all, I'm starting, in this case, I'm keeping theta. I'm not zeroing out theta, as in the Perceptron case. And again, it would be just easier technically to deal with it this way. So I'm assuming that I'm initializing theta to n, the number of features, and I'm initializing all the weight vector to all ones in this case. The prediction is 1 if the dot product is greater than theta, otherwise it's 0. If I make no mistakes, do nothing. Again, it's a mistake-driven algorithm. And here is how I change the weights. I update the weights. If the function is positive example, but I made a mistake, I thought that it's below theta, then I'm increasing the weights just like before, but now I'm doubling the weights. Now, I'm talking about the case where the feature vectors are Boolean, so I'm only touching those weights for which xi is active, and I'm doubling them. Before, I added something to them. If I made a mistake on a negative example, I'm dividing it. Now, I'm using here 2 just because it's easier. In practice, in fact, you will not use 2. You'll use 1.2 or something closer to 1. But really, the constant doesn't matter for nothing beyond. In practice, it does matter. For the analysis, it doesn't matter. So we're going to leave for 2. OK, so basically, it's a very simple algorithm, just like before. Notice that if I were to learn this junction, someone told me that I'm learning this junction, I could simplify this learning algorithm further. I could say, you know what? This step that you call demotion, a mistake or negative example, instead of dividing by 2, you can just zero out the weight. Why is that right? Why is it true to do it? Which means it's not there. This variable is not in the disjunction, so you can just eliminate it. But this is a special case for disjunction. In general, what I want to do is divide by 2. And then it will produce a linear function. OK, so this is some intuition, an example that will give us an intuition for the algorithm. So again, I'm assuming that I have, say, 1024 variables. My theta then is 1024, and this is my initial weight vector. And the target function is a disjunction in this case. It's a disjunction over 4 variables, x1, x2, x1023, 1024. OK, so let's see what happens. So I'm starting with this all ones as a positive example. The dot product is going to be 1024, right? Because it's all 1 times all 1. I'm not going to make a mistake. Nothing happens. My next example is all zeros. It's a negative example. I'm going to predict it negatively, right? So I did not make any mistake. No change in the weight vector. My third example is a lot of 1s, but all in the middle. not the first two and not the last two. So because it's not all of them are 1, the dot product is still less than 1024, right? Because I have all 1s times something that is not all 1s. So I have less than 1024 in the dot product. So I'm predicting negative. Sorry, I'm here. I'm predicting negative, but it's a negative example, so I'm fine. So the first 3 examples were uninteresting. I did not make mistakes. The next one is this. I have x1 is on, all the rest are off. This is a positive example, right? But I predict negative because the dot product is going to be 1. So I'm going to change the weight vector. The way I'm going to update this weight vector is I'm duplicating the first weight. So now I have 2, 1, 1, 1, 1, 1. Next example is something similar to it. I have x1 is on, and a few bits in the middle are also on. Again, it's a negative example. Sorry, it's a positive example because x1, I predict negative. And I'm duplicating a few of the weights. x1, w1 is now 4. And a few others have been duplicated. And so on. Next time, x1 is also on, so it's going to reach 8. And so on. So you can see that relatively quickly, about log n steps, log n over 2, which is just log n minus 1 steps, x1 is going to reach 1024, and we're not going to make any more mistakes because of x1. You see that? Questions? Is it clear? Okay. And you know, the same thing is going to happen with other variables. So this is kind of an intuition. Notice, it's very easy to see in the case of disjunction, the same algorithm is going to learn conjunctions. Thinking about a conjunction as a linear function in this case is a little bit harder. You need 256, for example, or one option is to have 256 on the important variables. So it's a little bit harder to see why this algorithm is going to learn it, but it will. Okay, so what I'm going to do is I'm going to prove that this algorithm is a good algorithm, but I'm going to prove it just for a very special case. As I said, the general proof, unlike perceptron, here the general proof is difficult. So let's prove the following thing. What I'm going to prove that on k disjunctions, this algorithm is going to make k log n mistakes. Think about it. It's a very, very good property, right? Because it scales only with k and only logarithmic with n. So in order to do the analysis, I'm going to split the number of mistakes to 2 types of mistakes. U is going to be the number of mistakes that we make on positive example. V is going to be the number of mistakes we make on negative examples. So let's analyze U first. So my claim is that U is bounded by k log 2n. Same thing. Why? Anyone care to try to analyze? So the key thing that you have to think about is, okay, so you made a mistake, and you're going to promote some of the weights. You make a mistake on positive, but then you make a mistake on negative, and you will demote some of the weights, right? So weights will go up, some weights will go up, some weights will go down. Why would it be the case that I will stop doing this process at some point and will not, you know, have to keep on promoting, demoting the weights? Yes? Okay, so that's the key point. So the key point is that a variable that is good, that is important to the disjunction, I may promote it because I see it on in negative examples, but I will never demote it, because I will never see it on in negative examples. Right? It will never, a good variable will never be on in a negative example. Because if it's on, it's not a negative example. That's the key thing, right? So basically, a weight that corresponds to a good variable is only promoted. Everyone agrees with that? If we agree with that, then it's easy, right? Because when these weights that correspond to a good variable reaches n, we will not make more mistakes on positive examples. So the worst case could be that someone supplies the stream of examples to me such that every good variable is on by itself. So I have to do log n step for this guy, and then separately log n step for this guy, log n step for the other guy, k times. That's the worst case. In the better case, they will be on together sometimes, and therefore I'll promote them together, I'll save. But the worst case is that I'll have to do it k times up. So I'll have k times. The log 2n is log n plus 1. And I think I need to exceed n. This depends on whether I want to do equal here or not equal. But everything in computer science is plus or minus 1, so it's fine. So that's u. Okay, so now we have to do v. Now we have to count how many mistakes we're going to make on negative. So I'm claiming that the number of mistakes on negative is actually related no more than twice the number of on positive. And here the argument is a little bit more subtle. So we're going to look at the total weight, right? So the total weight that we have in the weight vector starts with n, right? Because I'm starting with all ones. What happens to the total weight? So let's think a little bit about it. So let's assume I made a mistake on a positive example. What happens to the total weight? It increases, we agree on that. By how much? It doubles, no more than doubles. But if I want an additive thing, by how much will it increase? True that it doubles. But I want to know how much is that? At most. Why? What was the total weight before I made this mistake? N, exactly n, less than n, more than n? Less than n, right? Because I made a mistake. But it could be a little bit less than n. All this is going to be doubled, so I'm not going to add more than n. Right? So total weight at time t plus 1 is what I had before plus n at most. I cannot add more than n because before I had less than n. Otherwise, I wouldn't have made a mistake. Okay? So that's the case of positive. What's happened in negative? If I made a mistake on negative examples, what happens to the total weight? It goes down. Right? We divide it by 2. What does it mean? By how much we decrease it? N over 2. I hear n over 2. N over 2 first. So less or more than n over 2? I'm decreasing it by less than n over 2 or more than n over 2? What was it before I made a mistake? It was more than n or less than n? Okay, so so I'm making now a mistake on a negative example. If I made a mistake, it means that it was more than n. Otherwise, I wouldn't have made a mistake. It was more than n, and I divided by 2, so it's more than n over 2. So now it's going to be less than this minus n over 2, because I subtracted more than n over 2. Okay? Again, so here I'm adding no more than n. Here I'm subtracting more than n over 2. Right? And this together gives me this equation. So the total weight is positive always, right? Because I'm starting with 1, 1, 1, 1, and I'm just multiplying, dividing. And so it starts with n. U times, U is the number of mistakes on positive. I'm adding n or more. V times, I'm subtracting n over 2 or more. So it's less than this. So basically, you see here that u plus 1 times n is greater than v times n over 2. Which means that v is less than twice u plus 1. Okay? Really simple analysis. So together, this together with the fact that we showed earlier that v is less than k log n plus 2n, we get this. That u plus v, which is the total number of mistakes, is bounded by this. Which, if you really think about it, it's somewhat magical. The magic thing is that this works beyond conjunctions, and we're going to quantify it a little bit more next time. So I'm going to, but in general, this has something to do with the sparsity of the data. It says if your data is the sparsity of the function space. If your target functions are very sparse, you don't care about a lot of the variables. You just don't know which you care about. This says here is an algorithm that can learn with complexity that depends on the number of active variables, not the number of variables you have in general. Okay, so summary, what have we done? So we talked about two algorithms. We talked about the cases of real-valued feature spaces or Boolean feature spaces. And the reason I make the distinction is because the algorithms become simpler when it's a Boolean feature space. And it's a very, very important case. So we might as well think about it separately. We have real-valued hypotheses. In all cases, we have a prediction that is, say, plus or minus 1. And we predict if the dot product is greater than a threshold. Again, I'm formulating it now with the case of theta. So we had, and the update is done in a mistake-driven way. So if I don't make a mistake, I don't update. So we had two algorithms. One family of algorithms. At this point, we have just one representative, which is the perceptron, is doing this way. W is the previous W plus R yx. Ryx. And this is the case of the Boolean features, where I'm just touching those dimensions where xi is on. And we also had a multiplicative case, where I can think about it, W is W times e to the power of yi. So it's, instead of e, you can put 2 there, or any other thing that you want. So basically, either I multiply W by something, or I divide. If y is positive, I multiply. If y is negative, I divide. And again, we can write it for the case of this. So by the way, this is by now an old algorithm, but relatively recent to good machine learning algorithms. And we'll see that there's a lot of variations. Okay, so before we finish, I want to talk about, so I gave you two important algorithms, but we talked about the vanilla versions of them. The vanilla versions of them is really important and easy to analyze. This is not the version that you will actually use in practice. So when I say that Perceptron is a very good algorithm, and competitive with anything else that you will ever try, at least as of today, I don't mean the vanilla version, because the vanilla version is going to be okay, but it's not going to be competitive. You have to do a few tweaks in order for it to be competitive. And I want to talk about a few of the tweaks. So some of them, some of them are really necessary. The notion of regularization, which is the next slide that I'm going to talk about. And we kind of waved our hands around why we need regularization to support better generalization. We're going to justify it more rigorously a little bit later in the class. There is another important case for practical purposes, or sometimes important, and this is the notion of I want my algorithm to provide a probability rather than to provide a really valued number that I don't understand, the dot product, or just 0, 1. So sometimes you want to convert this to probability for good reasons, because you want to use it as a component in other algorithms, for example, so you need to interpret it somehow. And it's very easy. So you can basically you can assume, we are talking in the Boolean case, that the probability of y being positive, given the example, is 1 over, I just wrote it with -1 here, 1 plus e to the minus wx times some constant. This constant can be tuned on some set-aside data to give you a good or reasonably good probability distribution over this. The question of how exactly to tune it and so on, I don't want to get into it. I actually saw some figure here, but I don't want to get into it now. I want to move to the more important things. So there are two really key modifications that you want your learning algorithms to. You want to augment Perceptron and Winnow with to bring them to state-of-the-art algorithms. And the first one is to really think about the future, right? So we analyze Perceptron in the mistake-driven case. But so we know that it's going to be mistake-bounded case. Sorry, we know that the mistakes are going to be bounded, but when will the next mistake come? Or when I give you now an example, do you know whether you're going to make a mistake on it or not? Or do you know what's the probability that you're going to make a mistake on it or not? So the analysis that we provided, that is very simple and beautiful, doesn't provide an answer to this question. But you want an answer to this question, right? You want to know, okay, what's the probability I'm going to make a mistake now? So what we need is we need to be able to convert these mistake-bound guarantees to what we call here PEC guarantees, which we haven't defined yet. But basically, the idea is to tell me how will I behave in the future. And the question is how to convert it. And the first modification to Perceptron is a modification that aims at exactly converting it to an algorithm for which we can say this. We can talk about the probability of making a mistake in the future. So since this is the last minute or two of the lecture, I can ask you the question, how would you do it? Right? So really what you care about is you want to be able to depend on the number of examples seen rather than the number of mistakes. And the intuition is that if you've seen a lot of examples and you were okay on these many examples, you'll be okay in the future. Everyone buys this intuition? So how can you take your mistake-bound algorithm, Perceptron in a box, and convert it to something like that? Any ideas? Or is it possible to take this Perceptron in a box and guarantee to me that at some point it will be okay? It will look at a lot of examples and make no mistakes on them. Is it guaranteed? Yeah.
The number of mistakes is bounded.
So basically, the simplest way would be to say, of course, at some point, I'm going to run it so many times until I exhaust the number of the mistake bound. After that, I'm good. Right? And we want to do something that is a slight variation of this. And this is what average Perceptron is going to do. So what we're going to do is we're going to do this. We're going to wait for a long stretch without mistakes. And the claim is that there must be one. If there isn't one, it means that you made a mistake. You made one step toward the mistake bound. You keep on going. And what I want to do is I want to use the hypothesis that I have at the end of this long stretch. Because for this hypothesis, I know that it's been consistent with a lot of examples, and it's probably good. What average perceptron is going to do is actually return a weighted average of this protocol. So it's going to run perceptron until it makes a mistake. When it makes a mistake, it puts this hypothesis to the side, updates it, and keep on running. When it makes a mistake, it takes this hypothesis, put it on the side, and keeps on running. And at the end, it returns a weighted average of all these hypotheses, where the weights are a function of the length of the no-mistake stretch. So if you kept your hypothesis for a long time before you made a mistake, you want a high weight. If you immediately made a mistake, you want a low weight. And this average of a lot of outputs of perceptron turns out to be not only a good algorithm, but even something that we can prove has good guarantees in terms of generalization. Okay, so this is where we're going to start next time. See you Thursday. Were you here at the beginning of the class?
What? Yes.
I talked about it.
Because I started very earlier, so I used Word to do that.